Hello, my name is Roberto, and in this recitation we will discuss how to solve a problem with a minimum amount constraint in SAS. The problem that we will use as an example comes from Winston's Operation Research book, and it goes like this. There is an auto manufacturer that is considering manufacturing 3 types of cars: compact, mid-size, and large, and each car has a certain requirement of steel. For example, the compact car needs 1.5 tons of steel, and also a certain requirement in terms of hours of labor. For example, the compact car requires 30 hours of labor. The interesting thing here is that this problem also tells us that for the production of a car to be feasible economically, at least 1,000 cars of that type must be produced. What this means is that you can decide to do 0 compacts or 0 mid-size or 0 large, or you can decide to do 2,000. But what you cannot decide to do is to do 1 or 2 or 10. It is a 0 or 1,000 plus kind of constraint. And the objective is to maximize the profit of the company. So let's see how to solve this in SAS. So here we are in the web-based interface for SAS Studio. And this is the model that I have prepared for solving this problem using an algebraic notation and ignoring completely the minimum amount requirement that they specified. I have a decision variable, x1, for the number of compact cars that I will make. It's an integer because I'm not going to do half a car, and it has to be either 0 or positive. It cannot be negative. I cannot do -2 cars. Same for the mid-size cars is x2, for the large cars is x3. My objective function is to maximize the profit, which is 2,000 times compacts, 3,000 times mid-size, 4,000 times large. So this profit is given in thousands. I have a constraint for the steel available. I have 6,000 tons, and this is the function that expresses how many tons I'm using based on the decision variables. I have another constraint for the labor available, which is 60,000 hours, and this is the expression that gives me how many hours are being used depending on how many cars I decide to make. I solve the model and I print the 3 decision variables. Let's solve this. All right, nothing new here. This is just to give us a baseline. I make $6.28 million in this solution because this is given in thousands. And I decide to do 570 small cars, compact cars, right? And 1,700 mid-size cars. Now, what is the problem here with this solution? We ignored the minimum amount constraint. We are not allowed to do 500 compact cars. It has to be at least 1,000, right? So in the future, we will include this constraint in the model. Before we do that, however, let me show you the indexed solution to this same problem. The one that you just saw here is algebraic, x1, x2, x3, very straightforward. Let's see the indexed version now. Let me replace this algebraic solution with the indexed solution. I am defining a set of models. Compact, mid-size, large are the members of that set. The steel requirement for each member of the set, 1.5, 3, and 5. The labor requirement for each member of the set, 30, 25, 40. The profit yield expected, which is given in thousands, 2, 3, and 4 for each member of the set models. And I have my decision variable, which is also 1 for each member of the set. Has to be an integer, has to be equal to or greater than 0. I have my profit function here given as the sum across models of my decision variable of how many cars to make of each model times the profit that I can expect from selling a car of that model. And the constraints are given here also: the number of cars I make of each model times the requirement of steel for that model, same for labor, the number of cars I make of each model times the labor requirement for that model, and they have to be less than the respective limits of steel and labor. And when I solve this and I print the decision variable, we see that the solution is the same as before, 6.28 million, and I make 570 as before, and 1700 of this one, just as before. This is just for you to see now how to do this in an index notation. So far, nothing here should be new to you. This is all stuff that we have seen in previous recitations. Let's see now how we can include the constraint for a minimum amount of production for each model. Here we have the model for this version of the problem. We define a set for the models with the 3 elements we saw before. Steel requirement is the same as before. Labor requirement is the same as before. Profit yield is also the same as before. Here's where the changes start. We have a minimum run parameter that we define as 1000 for each model. Now, there is no reason why this has to be the same for all models. We can make 500 for compact and 1000 for mid-size and 200 for large, for example. And here we have a sufficiently large number, which here is defined as what, 100,000, which we know that our production levels are never going to reach 100,000, so we use that value as an M. And we have a new decision variable besides the one that we saw before of how many cars of each model to manufacture. We have this auxiliary or ancillary binary decision variable, which is going to be 1 if I am making any car at all of a given model, and it's going to be 0 if I'm making no cars of that model. My profit expression is the sum of the products of profits times the number of cars I make of each model. The constraint for steel and labor are the same, and here's where we have another change compared to the previous version of the model that we saw. We add this constraint here, which should be familiar to you, which is a binary constraint for, it's a constraint related to the binary variable for use. You may remember from our recitation about fixed charge, where we have this expression that says that x has to be equal to or smaller than m times y. And what this means is that your x can be 0, in which case your y would be 0. But if your x is bigger than 0, then because of this multiplying m here, which is very big, your y has to become 1. So if you're producing any cars at all, your y is going to become 1. This is kind of a switch constraint. We've seen this before. If this sounds unfamiliar to you, you may want to play again the recitation about the fixed cost or fixed charge that we saw before, because this should not be new by now. This is the actual constraint that is new. And this constraint says that for every model, I have a minimum run, right? A run minimum. I'm calling it run minimum, the constraint. And it goes as follows. The number of cars that I make for each model should be equal to or greater than the minimum run for that model times the binary flag of whether I'm manufacturing that model. Let's see how this works. If I decide to make 0 cars of a given model, x is 0 and y is 0, and 0 is equal to 0, so it's satisfied. But if x is not 0, it's positive, then it has to be bigger than the minimum run, which is like 1,000, for example, times 1. 1,000 times 1 is 1,000, so it has to be equal to or greater than 1,000, which is exactly what we're looking for, so this works. Let's now run this. You remember before we used to make 6.28 millions, and we were doing something like a little less than 600 compact cars. Let's compare it with that solution now. If you see, we're making less money now. We're making 6 millions versus 6.3 in the past. Why are we making less money? Because when you add constraints, your solution is not going to get better. It's going to stay the same or get less good, it's going to become worse. And you can see that the decision is to make 2,000 mid-size cars. I'm not making any compact. Why? Well, because I was so far from making the required minimum that it would take me even farther from my optimal. So this is the best I can do given the new constraint. Now, one of the things that I would like you to do, I would invite you to do, is to play with these models. And you should not be afraid to make mistakes. So let's do that together. For example, what if we had a maximum amount constraint? You remember I just told you that the company said, hey, you cannot produce less than 1,000. Okay. How about I am given a maximum constraint that I cannot make more than 1,900 mid-size cars. So let's say that my minimum, I say I cannot make, I'm going to play with these numbers a little bit. I'm going to say, how about the minimum run you can do for a compact is 750, right? The minimum you can do for a mid-size is 1,000. The minimum you can do for a large is, let's say, how about we say 500, right? Well, let's make it less, 200. And let's add now a new parameter that I'm going to call max run. This is the most that I can make. I know that for compact I want to make it 19, and let's say that for this one I want to make it no more than 1,500, and let's say that for large, I'm just playing here with the numbers, I cannot make more than 1,000. All right, so my production now has to be between 700 and 1,500 for compact, between 1,000 and 1,900 for mid-size, and 200 to 1,000 for large. Now I have to include this max run here in a constraint, also in my model. Let's see, where would I have to put that? How about I add it here as a constraint that says a run max constraint that applies to each model, where my produced amount has to be less than or equal to the max run parameter that I have given above. And I don't have to multiply times the binary variable, because here's how it would work. If I make 0 cars, that's less than my maximum. And if I make a number that is bigger than 0, as long as it's less than the maximum, I'm fine. So I think this should work. Let's run this and see if it actually goes through. Oh, we have some errors here. No errors. Excellent. Great news. Great news. So if we had some errors, we would see them in the log, and we would analyze those errors. We didn't get errors, so actually we're making 6 million, which is the same as before. And the decision here is to make 1,500 mid-size cars, as opposed to 2,000 that we were doing before. And 750 compact, which, if you remember, this is the minimum we are allowed to do in compacts. So this gives you an example of how you can play with the model. If, for example, you're asked something like, okay, what if there is a maximum to, and you think about it, then you add the line. I wasn't sure that this was going to work, but you should not be afraid to try things and be wrong. That's how people learn. All right? Okay, finally I want to do a combination. In an earlier recitation, we saw how to do a fixed cost. In this recitation, we saw how to do a minimum amount. How about we have a problem now that has both a minimum amount and a fixed cost constraint? This is the code that I have prepared for this variation of the problem. This part is the same: the set definition, the steel requirement, labor requirement, profit yield, minimum run. This part is new. I am adding a parameter that is a fixed cost for each model, and I am saying, if you are doing any compact car, there is a fixed cost that you have to pay of $100,000. That 100 is in thousands, so it's 100,000. If you're doing mid-sized cars at all, you have to pay $1.5 million in fixed cost. And if you're doing a large car, there is $250,000 fixed cost. Okay, so I add that parameter there. The other modification that I do to the problem is in the objective function, where to my profit expression, besides the profit obtained for each model of car that I sell, times the number of cars in that model, I have to subtract the fixed costs. And the fixed cost would be the binary variable that is a 1 if I am producing for a given model, times the fixed cost of producing for that model. All right? And there's no change in the constraints. Notice that in this model I don't have the maximum amount constraint that I had showed before. Let's run this. We could have it by that way. We could have the maximum amount constraint too. This is something, building a model is done in layers. It's like building a house where you have first the floor, then the walls, then the roof, then the windows, then the toiletries, and like the kitchen, and so you do it little by little, not in one single move of the magic wand. You can see that in this solution we're making 4.5 million, and the decision is to produce 1,200 large cars, no mid-size cars. Now, why are we not making mid-size cars? If you remember, in the previous solutions, the mid-size was the favorite model. Well, the thing is that here we have said, if you're making mid-size, you're paying a lot in fixed cost. You're paying 1.5 million. When would this be plausible? For example, if you have a factory that is used to produce only compact and large cars, and then now this mid-size is a new model, and you have to buy the new equipment and get it ready to produce this mid-size model, then there is a higher fixed cost of producing that car. So this is a plausible scenario. So I hope you had fun in today's presentation. I hope you learned, and I invite you to play, maybe now making a combination that has both minimum and maximum, and also fixed cost.